congrats for the presentation. I think it was very good and very interesting. I have two questions.
Yeah.
You have how to guarantee that your method is adhering to the borders. For example, in this image.
No, the first thing, as I mentioned, is that we should guarantee that the borders they are there. That's the first step. And of course, it depends on the image and the image segmentation method we have created, and so on and so forth. And then the second thing is that the cost function should be sensible to such errors. For instance, because if we match a lot of good, if we do a lot of good matchings here in the cost function, and we are wrong in some border regions, the point is that maybe globally the cost function is being optimized, but actually I'm getting wrong in the bad regions, because for human beings, if I am wrong here, it's easier, but if I'm wrong here, we can catch it quite fastly. The way we solve this problem in this situation, there are two ways. The first way is by using some multi-scale approach, where you try to match globally the objects, and then after you can optimize some different regions. For instance, if I optimize just the eye region or something like this, then we tend to improve the accuracy. And the second way is by interaction. I mean, maybe for many applications, just simply a nice way. For instance, when I show the model we use, maybe it's easier just to apply to have some good result, though not perfect. But the user, of course, he or she is not required to do scribbles in every image, and he or she just have to do some small clicks in order to get the final good result.
Second question is, what's the difference between the key graph and the random graph?
You mean random graphs, the theoretical definition of random graphs? Well, random graphs, they are mathematically well defined. They are defined by, you have to have the distribution of the edges, etc., etc. And for the key graphs, what I call key graphs actually is a way of remembering the idea of key points. If you look in the literature for object detection or something like this, you have the key points approaches like SIFT, SURF, Harris, and so on and so forth. And we are here defining an analogous of the key points, but using graphs instead. That's why what we call key graphs. Actually, there are simply subgraphs with some topology that is defined a priori, and our algorithms, they explore such topology. When I said, when I talked about the constraints, for instance, in order to look for the good key graphs, actually the algorithm tries to explore topology in order to speed up the decision. But they are just simply like this.
But the way that you connected the vertices is the same way that you explained in the beginning?
Yeah, and it depends it depends from the training set, because we define all these a priori. Sorry? No, they're not random. Nothing in the sense of course, we can pick randomly subgraphs in order to see if they are key graphs, and we do. There are two different. That's why I was asking. There's the mathematical concept of a random graph, and there's also the idea of exploring randomly the key graphs that I may find. And we actually do this because we have just simply a combinatorial explosion of possible key graphs. And what we do is to subsample this combinatorial explosion in order to find some good. We don't need to match all key graphs. That's the basic idea. When I'm looking for good matchings like this, let me show. When I'm looking for this object in the scene, I don't have to match all key graphs from the model. Actually, I have to match some key graphs, and if I am glad with the key graphs I have matched, I simply say, well, okay, I'm using this. Actually, we use some stochastic Hopf transforms or Ransack in order to find these key graphs. Then it's random in this sense. We don't match every graph. We just sample the possible key graphs, and if I am able to match some sampled key graphs, I am glad for detection. I think there is.
Thanks. Is there any kind of application to image compression of this kind of graph segmentation based method? Because, for example, for these graphs are essentially planar maps, and the problem of compressing planar maps is very well known. So
I am not aware. I don't know. Because the point here, maybe we can use, I don't know, just brainstorming now here. For this new approach here, what we have is that we will have estimation of the parameters that synthesize the attributes from the image. maybe should be we should also be able to simulate the models and then to reconstruct the image. But I'm simply throwing ideas here now. I don't know.
In the interactive segmentation application, how is the graph technique sensitive to the different scribbles?
We have done a lot of tests about this. We are glad it's kind of robust. We have compared, because there are some protocol experiments in order to compare this with graph cuts, etc., with different scribbles. There are some of the database. I don't remember if the Berkeley or some other. They have image segmentations with some different seeds, etc. And we have compared, and it works quite well. But it's an experimental result. I don't have a formula showing that it's robust or something like this. Experimentally, we are glad with this.
Questions? Roberto, when you have, I didn't understand well actually, when you have similar objects connected to each other, like the two horses that you showed in one of the pictures.
The two
horses that you showed in one of the pictures. How does your model disconnect them? I mean, do you need markers close to the boundary, or you actually don't need markers close to the boundary, right?
Yes, these are the marks that we have obtained. I really suppose these are the best results my PhD student obtained, and I'm showing the best results he obtained. But this is yes, these are the marks that have been used. Sometimes what we have is that, for instance, these small markers here, this is an indication that first he made the big scribbles, and then the method got wrong parts here, and then we have the small marks. Like this.
No, what I didn't understand very well is how the model can distinguish, for example, when you go close to the boundary between the horse. How can it distinguish that the regions of the small horse have to be merged together with the green?
The only thing that is sure here is that there are watershed borders here.
Oh yeah,
we are sure about that.
That's true.
We are sure that there are watershed borders here.
But then when you measure the properties of the regions, they are very similar.
Maybe, yeah. And it means that although they are similar, it's cheaper for the method, for the optimization algorithm, to map these regions to this model than to map to the other one.
I was just wondering that maybe you're exploiting some kind of distance to the marker. Maybe you're exploiting some kind of distance to the marker. I mean, between the region and the marker.
The coordinates are part of the attributes.
Okay, the coordinates.
Yeah. Okay. The coordinates, they are part of the attributes. That's why, if you remember the demo that I shown, that's why we need the click. Okay. You remember there was the model we used where the user made the first segmentation, and then Alexandre simply clicked on the other ones. This click provides us a shift in the model, a spatial shift in the model, and it's all we need in order to adapt all the coordinates and so on and so forth.
So in other words, if you have a tie in deciding which region, which marker will take in a region, then that tie is solved by the distance, probably, because of the coordinates.
Actually, it's implicit, because the coordinates, they are part of the attributes, which means that the cost function is taking into account both color, texture, etc., and the position, and spatial position.
But I mean, during the interaction, if it does not solve, so if you see an error, then you should click a new marker close to it.
Yeah. There are some situations, for instance, for medical images, we can explore more complex, and we have explored actually with Isabelle and Olivier Colliot, more complex spatial relations. For instance, symmetry. Mm-hmm. There are in some situations, you know that symmetrically, for instance, the lungs, they should be symmetrical. Then we can use this spatial relation symmetry as an additional...
to solve the ties.
Yeah.
And have you thought to use any classifier at the nodes of the model graph?
Here,
or you just
for the last approach I'm just mentioning, Actually, what we are going to have is that we are going to have statistical distributions of the nodes. Then we can use these for the classifications. We use classifiers actually for the key graphs, but because what we do is that from the model, we extract a huge, possibly huge set of key graphs, which represents the model. And then for each input key graph, now I'm not classifying anymore whole graphs, but key graphs. What we have to do is a pattern classification where each pattern is a key graph. Now, and actually, I think Marcelo used some key nearest neighbors or something like this. And now we have a new PhD student, Stefan, who is trying to adapt to some SVM or something like this. But it's simply a reduction of path recognition problem, because we want to segment to classify key graphs.
So great.
A key point is defined as a strong point in the image. How you define your key graph?
We define the topology, and we define key points, and we create key graphs as graphs from the key points. Then first we apply some key point detector, for instance Harris or Sister or something like this. And then we start creating the topology of the graph by defining some topology a priori. We want key graphs with three nodes and the direction. Simply we have to the orientation. This is the simple. There are some additional heuristics we put. For instance, distance, we don't know. We don't want key graphs larger than something and smaller than something. There are some heuristics in order to define this. But it depends on the application.
Any more questions? Okay, so let's thank Roberto.
I'm really grateful for everybody, Luciano, that invited me. Thank you very much.